Hey, this is my attempt at a sort of highlights reel of everything from the first semester of chemistry. Just really quickly, refresher run. All right, so I just kind of selected favorite slides from different lectures. All right, so first off, let's remember that chemistry is made up of, chemicals are made up of particles, particles of matter. And there's different names for different types of particles, and we can classify different types of particles of matter. So an individual element of matter, of a single element, is an atom. So you can picture those in the sort of particulate model. Those are always kind of represented as like single balls in a box, maybe. Some elements are diatomic. I'll remind you of the Hofbrinkels, and they are still a single element, but they contain two or more atoms. Diatomics are two atoms. There are some elements that contain more than two atoms, but it's all the same element. So if it's just consisting of one type of atom, then it's an element. All right. If it consists of more than one type of atom, it could be either a compound or a mixture. They contain more than one type of element. Compounds are different than mixtures because compounds, the atoms are actually chemically bonded or connected together. So like these two. Versus a mixture where you have the elements are separate from each other, physically separated. The particles are physically separated from each other. So compounds are still pure substances because they are all of the substances in this box are identical, right? All of the particles here are identical. So any box where you picture identical particles, elements or pure compounds, we call those pure substances. But if we have a mixture of elements or a mixture of compounds together in a single container or box, that's a mixture. Okay. And one more thing is that compounds, when you have atoms bonded together, and diatomics for that matter, anytime you have more than one atom bonded together, we call that a molecule. All right, so that's some terminology. States of matter, we've got solid, liquid, and gas. Solids are tightly packed particles. The particles are moving, but they're just vibrating just a little bit, but they're really very structurally connected. Versus liquids, where they're close together, they're touching, but they can kind of roll over each other. They're moving a little bit faster, which is why liquids can flow. They can take the shape of their container, but they still have a constant volume. You switch a liquid to a different container, the volume doesn't change. The shape will, but the volume won't. Versus gases, these are particles that are all far apart. They're moving very quickly. They're bouncing off each other. They're not sticking together. And therefore, they have both a flexible shape and a flexible volume. They can expand or contract to fit the volume they're in. There are various state changes between these different states of matter. Going from solid to liquid is melting. Liquid to gas is evaporation. And in order to do that, we have to add heat. So these are endothermic processes. Heat is going into the system. And then the exothermic process is when we're removing heat or cooling something, we condense gases to liquid and liquids freeze into solids. So some more vocabulary there. Reminders about different SI units for different things. So for time, seconds. For length, meters is the base unit. For mass, kilograms is the base unit. And for thermodynamic temperature, Kelvin is the Celsius is one that we use a lot as well. And then moles, we'll talk about moles. And so we know that each of these prefixes has a certain meaning. So like centi is 100th, so a centimeter is 100th of a meter. And then we can use these to do conversions between units using those prefixes. Always with unit conversion, we're starting with a given unit, and then we multiply it by a conversion factor where the desired unit is on top and the given unit is on bottom. So if we had 100 centimeters and we wanted that in meters, 1 meter is 100 centimeters, so on and so forth. All right, so here's some practice math, so I'm showing you those conversion factors. We call this process of using conversion factors dimensional analysis, or sometimes we just refer to it as unit conversion. And the way that we make these conversion factors is they come from equalities. So 12 inches in a foot. 1 minute is 60 seconds. And we can turn that into a ratio. The ratio equals 1 because 12 inches is equal to 1 foot. Anything over itself is 1. So that's why we can use it in either direction. We can flip it and use it either way because the ratio itself is technically equal to 1. Okay, so that's a little bit of math for us. When we are doing math in chemistry, it's important to use the correct number of significant figures. This represents our level of certainty of our measurements and our calculations. And so when we are measuring something in the lab, we want to include the measurement to one estimated, so as many digits as we can be certain of, and then one estimated digit. So it will depend on the accuracy or the precision of our measuring instrument. So if there are no markings on this 1 meter stick, we really can only estimate that it's between 0 and 1, so we can estimate it to the tens place. But on this measuring stick where there are markings every, let's see, centimeter, every millimeter. Nope, there's 100 centimeters in a meter, so there's every centimeter. So we can measure 60 here. It's definitely between 60 and 61. So we can estimate it between 60 and one place between 60 and 61. So 60.8 centimeters is a good. When we are doing math calculations with significant figures, just remembering how to identify sig figs, and it really just comes down to remembering which zeros are significant. Okay, they're not, if they're on the right side of the number here, if they're on the tailing end and there's no decimal place, they're not significant. If it's a number with a decimal place, they are significant after the decimal place, but only if they are after significant digits. So these guys here in the front, these leading zeros, you can consider them placeholders. They're not significant. They just tell us what, you know, how many digits to go out before we start seeing significant numbers. So these zeros in between and at the tail end after the decimal point are significant. The easiest way to think of significant figures is if you're going to convert that number to scientific notation, would those zeros be included or not? And no, they would not be included here or here. And then also when we do math, if we are multiplying or dividing, we round our answer to the lowest number of sig figs. If we are adding or subtracting, it's the closest space. The answer has the same number of decimal places as the measurement with the fewest number of decimal places. So it's going to the fewest number of decimal places, not digits. Temperature scales. There's 3 different temperature scales: Fahrenheit, Celsius, Kelvin. We use all 3, mostly Celsius and Kelvin though, in chemistry, and these are the formulas to convert between them. Celsius and Kelvin are just 273 degrees apart, 273.15, so you just add 273.15 to go from Celsius to Kelvin. Different chemicals have different properties. There are physical properties and there are chemical properties. Physical properties, think of adjectives that you would use to describe them, how they smell, how they look. Chemical properties, how they react. Intensive properties are things that are sort of innate, if you will, to the substance and doesn't change depending on how much of that substance you have. So like density is an example of an intensive property. It's also a physical property. It has to do with the mass and the volume, both of which are physical properties. We call it a derived property because it's mass divided by volume. And it doesn't matter how much copper you have, how much copper material you have, it's always going to have the same density. Copper has, that's an intensive property. Extensive properties are things like mass and volume. These different pieces of copper will have different masses and different volumes. Those are extensive properties, but they'll have the same density. Intensive properties. So intensive properties are useful for helping to identify substances. Let's put it that way, because they're kind of like a chemical fingerprint, if you will. Matter is made up of atoms, and atoms are made up of subatomic particles, the three major subatomic particles to know: protons, neutrons, electrons, and their charges and locations. Protons and neutrons are in the nucleus. Electrons are in shells that do not orbit in two dimensions like this, but it's a good, this is the Bohr model representation, a very simplistic representation. The number of protons is the atomic number, which is, I'll show you on the next slide where it's found on the periodic table. The electrons in a neutral atom are going to equal the number of protons, and the neutrons are going to add up with the protons to the mass of the atom. So we can write the atomic notation in this symbolic notation here, where we indicate the chemical symbol, and we know the chemical symbol for this is lithium because of the atomic number 3. It has 3 protons. If we go to the periodic table, 3 is lithium. The mass number is 7 because there's 3 protons and 4 neutrons. We add those together for a total of 7. And the charge, we don't usually put a 0 charge. If there's no charge, we just leave that blank. But to clarify here, there is 0 charge. This is a neutral atom because the number of protons equals the number of electrons. So 3 minus 3, 0. Isotopes are, I like to say, different flavors of an element. And the reason the iso in chemistry means same but different. So they're same in some way but different in another way. So isotopes they're the same element. So they, by definition, have the same number of protons, but they have different numbers of neutrons, which makes them have different mass numbers. So for example, there are 3 different isotopes of magnesium. They all have 12 protons, but they have different number of neutrons, which gives them different mass numbers. And the mass number is always a whole number because it's just protons plus neutrons. But when you look at the periodic table, you'll see that magnesium has a mass of 24.305. That's the average atomic mass, and it's a weighted average that's based on the abundance of these different isotopes. So magnesium 24 is the most common isotope, the most abundant, which is why the mass is very close to 24. So this is just how it's calculated. All right, so here's the periodic table. It's divided into columns, vertical columns, and horizontal rows. The rows we call periods, and the columns we call groups or families, and they're numbered. Generally, you have the chemical symbol, sometimes the chemical name, the atomic number, and it goes in order of atomic number, right to left. So 1, 2, 3, 4, 5, 6, 7, 8, 9, keep going. And then the atomic mass, which sometimes it's on the top, sometimes it's on the bottom. Different periodic tables will be formatted differently. We've got our different names of the different families. So the periodic table is arranged in this interesting shape because it puts all elements that have similar qualities, similar chemical characteristics, or similar chemical properties in the same column together. And we call those families. So column 1, alkali metals. Column 2, alkaline earth metals. Then we've got the transition metal block here. We skip over. So in the green, these columns 1, 2, 13 through 18 are known as the main group elements. And then we have the transition metals and the lanthanides and the actinides. Some other groups to know: 18 is the noble gases, or I sometimes call this group 8A. And 17, or group 7A, is the halogens. I never use these terms for 15 and 16. So just like we have isotopes, atoms can have different numbers of neutrons. They can also have different numbers of electrons. We don't call those isotopes, we call those ions. So when there's different numbers of electrons, or an uneven number, basically when it has a charge. If there's a charge, we call it an ion. So ions can be positively charged or they can be negatively charged. Negatively charged are called anions. Positively charged are called cations. Anions form when an atom gains an electron. So in this case, chlorine gains an electron. 1 electron, it ends up with, so then it has 1 extra electron, so that's 1 extra negative charge. Sodium, in this case, loses an electron, and therefore it has an extra proton, more protons than electrons, so it has a positive charge. It's a little bit counterintuitive, When you gain electrons, the charge goes down. When you lose electrons, the charge goes up. So when we can use the periodic table actually to predict the charges, because again, these elements are grouped based on similar chemical properties, and we'll see it's based on similar electron configurations. So all of the group 1 elements, you notice, have a 1+ charge. All of the group 2 elements have a 2+ charge. Transition elements do some funky stuff and have multiple charges. But if we skip over here to the main group, 3+ on our aluminum. Carbon can go either way, actually, and then 3-, 2-, 1-, and notice the noble gases do not form ions. They have a full valence shell. So when we are making compounds, putting atoms together, they can either form ionic compounds or covalent compounds. Ionic compounds form when you have 2 ions of opposite charges that are attracted to each other, right? Opposites attract, opposite charges attract. So a positive ion, and notice that everything on the left, all of the metals are on this left side of the periodic table. They always form cations. They lose electrons, and the metals form anions. So that's why ionic compounds are usually made of a metal and a nonmetal, a cation and an anion. And when they come together, we simply just, the name of it is just the name of the metal plus the name of the nonmetal, but change the suffix to "ide." So a magnesium and fluorine, when they come together as ions, when they form ions and come together, it forms magnesium fluoride. Now, magnesium has a 2+ charge, and fluorine has a 1- charge. And so when we put them together to make magnesium fluoride, we need those charges to cancel out. Magnesium fluoride is not charged. Ionic compounds are neutral. And so there's sort of 2 different ways to think about forming this compound is the puzzle piece method. So you can think of the 2 charges and of the magnesium and the 1 charge of the fluorine, or the crisscross method. So just kind of showing these. You need 2 fluorines to balance out the magnesium charge. And the crisscross method is moving the charges down and making them subscripts. So either way you do it, you would end up with magnesium fluoride, has the chemical formula MgF2. And that subscript tells us that there are 2 fluoride ions for every 1 magnesium ion. All right. We also have polyatomic ions. There's a whole bunch of those. It is helpful if you memorize them. I do give you them on the test reference sheet. And when we have polyatomic ions, these are ions that contain multiple atoms. And so if we need a subscript for them, we just have to remember to put parentheses around them, consider them like a single unit. Even though it's nitrogen and 3 oxygens, it's 1 ion. So this would be magnesium nitrate, for example. All right, covalent compounds are the opposite. They are nonmetals plus nonmetals. So nonmetals are the ones that we say they form anions, all right? They have nearly full valence shells, we'll get to that, but when they get together, there's not an electron loss or an electron transfer. It's a sharing situation. So with covalent compounds, we name them differently as well. So with covalent compounds, we have to use these prefixes because in covalent compounds, their chemical formula is not determined by canceling out charges. So like magnesium nitrate, it can only ever exist. You can have 1 magnesium and 2 nitrate ions. There's no such thing as like MgNO3 or MgNO3 subscript 3. There's no other versions of that compound, okay? But there are many combinations of carbon and oxygen or nitrogen and oxygen. And so we have to use prefixes when we are naming these compounds because we can't just call it carbon oxide because then this would be carbon oxide. So we have to use prefixes. So we use these Greek prefixes, I believe. So this would be carbon monoxide, mono for 1, carbon dioxide, di for 2, and this would be dinitrogen pentoxide, 2 nitrogens, 5 oxygens. So the name really tells you what the subscripts are. The one sort of like exception is we don't use mono on the first atom. So like if there was 1 nitrogen, it would just be nitrogen pentoxide, not mono nitrogen pentoxide. So mono, the prefix mono, we only use on the second element, but all the other prefixes we use either way. Alrighty, so when we write out the formula, oops, for we can draw out, we can write out the chemical formula for a substance. So like C8H10N4O2, this is actually caffeine. It means it has 8 carbons, 10 hydrogens, 4 nitrogens, and 2 oxygens. So the mass of this single molecule would be adding up all the masses of those atoms together. So the unit of atoms is an atomic mass unit. So this would, one molecule would weigh 194 atomic mass units, but that's really, 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 really tiny. We don't work with, we can't in the real world work with values that are that small. And so we use this conversion factor to convert the formula mass into grams, essentially. And that conversion factor is Avogadro's number, 6.02 times 10 to the 23rd. And we give this number a name, so we don't have to say 6.02 times 10 to the 23rd. We call it a mole. It's just like being like a dozen is a mole. Or a dozen is 12, so 6.02 times 10 to the 23 is a mole. So the molar mass is when we figure out the molar mass the same way as the formula mass, except that it's in grams, not atomic mass units. Okay, so we can do conversions from moles to number of particles using Avogadro's number and the molar mass. So the sort of introductory mole train map, it looks like this. So moles are the central unit of chemistry. We tend to work with moles of substances. So we can, if we know how many particles we need, we figure out how many moles and then what the mass would be. Or if we know the mass, we can figure out the moles and then the particles by using the molar mass as conversion factor between grams and moles, and Avogadro's number as the conversion factor between moles and particles. Atomic structure. So we had that Bohr model before where it looks like, planets orbiting a sun, the nucleus, the electrons orbiting the nucleus. That's a very simplified model. What Bohr did get right was that electrons do occupy these different energy levels, and the energy levels are different distances away from the nucleus, but they're not two-dimensional planetary orbits. They're actually like three-dimensional orbitals with different shapes and different like three-dimensional spaces. So it's a little bit more complicated mathematically and visually. And that each of those energy levels is actually divided up into different sublevels. The larger the energy level, the more sublevels it has. And those sublevels are divided up into orbitals. So you can kind of think of like the energy level as like the floor of the building and the sublevel as like the unit, like apartment unit, and orbitals is like the number of rooms. I don't know. So these are another way to sort of visualize these different energy levels and orbitals. So this is an energy diagram or an orbital diagram, and you can see these different energy levels are color-coded. So energy level 1, N equals 1, energy level 2, so energy level 1 has 1 sublevel, energy level 2 has 2 sublevels, energy level 3 has 3 sublevels, so on and so forth. The sublevels are S, P, D, and F. So energy level 1 has just an S sublevel. Energy level 2 has S and P. And you'll see that S has only one room. It has just one box, all right, one orbital. These boxes are called orbitals. The P sublevel has 3 orbitals. The D sublevel has 5 orbitals, and F has 7. It goes up by odd numbers, right? And each sublevel, each orbital, you can see can fit 2 arrows. Those arrows represent electrons, and they're pointing in different directions to represent their different spins. So, for example, what I have here is the orbital diagram for an atom of phosphorus. Phosphorus has 15 protons, therefore an atom has 15 electrons. So if we fill this in order from lowest energy and we move up, we end up with this orbital diagram. So we've got 2 in 1s, we have 2 in 2s, 6 in 2p, and so on and so forth, up to 3 uh, electrons in 3p sublevel. So this is called the orbital diagram. This is the electron configuration. We can shorten the electron configuration and do sort of a shorthand notation where we use the noble gas to represent that noble gases electron configuration, and then just add on the extra electrons. So the noble gas before phosphorus is neon, so neon plus 3s2, 3p1, 2, 3. And we can actually use the last part of the electron configuration to quickly find things on the periodic table, because the first two columns are the S block. So everything in column 1 is going to end in S1. 1s1, 2s1, 3s1, 4s1. Everything in column 2 is going to end in S2. And in the purple block over here, these are this is the P block. So these are going to end in P1, P2, P3, and so on and so forth. And the transition elements here are the D block. So this is just sort of like a quick recap on electron configurations. Also in that same vein, we have quantum numbers, and quantum numbers are sort of a way to give an address to a single electron. And this is really what physicists do in the physical side of chemistry, and understanding, I'm not getting into the part about how electrons give off photons of energy. When you add energy, the electrons can jump to a higher energy level, to a higher orbital, and then they can fall back down and release energy in the form of photons or light. And you can calculate how much energy each of these electrons has, but we don't need a refresher of that. Just a reminder that these quantum numbers just represent the address of a given electron. Each electron has a different amount of energy, so each electron occupies its own space, so its own energy level, orbital, sublevel, and orbital. And we have a system for naming those. So the 4 quantum numbers, the energy level 1, 2, 3, 4. The sublevel is SPD, but we use numbers instead. So S is 0, P is 1, D is 2. The orbitals are named like negative L to positive L. So for the p orbital, it's got 3 orbitals, and the p number is 1. So it goes from -1, 0, +1 in that order. And so, for example, I have the 4 quantum numbers of this electron right here. The address for this electron that I have circled, it is in energy level 3, it is in the p sublevel, and it is in the 3rd or +1 orbital, and it has a positive spin, so it's +1/2. All right, so these electron configurations, understanding electron configurations, is kind of key to understanding chemistry, how chemical reactions happen, because they pretty much all have to do with electrons. Bonding, for example, how those ionic bonds and ionic compounds and covalent compounds form, all has to do with electrons. It's those, but really it's the outermost electrons, because these are the ones that are, on the surface, outermost, and so they're the ones that are going to get lost, gained, or shared. So atoms that are most stable are the noble gases. The noble gases do not form ions because their valence shell is full. Their outermost energy shell is full. They don't want to get rid of any electrons. They don't have room to add electrons, so they sometimes might get together and share, but really they're very non-reactive. However, group 1 over here and group 7A over here are very reactive, and that is because group 1, they just have that one measly valence electron, and they are happy to get rid of it so that their next shell is full. And the group 7A elements have 7. They really, really want one more. And so basically all bonding and chemistry kind of comes down to electrons and atoms sort of seeking that full valence shell. So we call that the octet rule, because most atoms have a full valence shell when they have 8 valence electrons. The 2 exceptions are hydrogen and helium that only have an s orbital, so they're full with 2. All right, so just to show you here, sodium, for example, when it loses its 1 valence electron, it loses that 3s. It now has this electron configuration, which is the electron configuration of neon. And when chlorine gains an electron, it now has the same electron configuration. The chlorine ion has the same electron configuration as argon. So they're trying to be like the noble gases, is what I like to say. But the chemistry term is that they become isoelectronic with noble gases. They're trying to have the same electron configuration. All right, and that so all bonding, you've got ionic, covalent, and covalent bonding. In ionic bonding, somebody loses an electron, somebody else gains an electron, and then they're attracted by their opposite charges. Sharing electrons also occurs in that valence shell, and have little smiley faces in the nucleus to show you that they're happier that way. Next, alrighty, electronegativity. So this is the strength of the pull that an atom has on electrons in a bond. And so the four big electron hogs, fluorine is the biggest electron hog. There are these arbitrary sort of values, numerical values for electronegativity, but really just know the trends that fluorine is the most electronegative, and these four guys are the biggest electron hogs. In other words, when they are in a sharing contest with another atom, all right, they tug harder and they win the tug of war. Sometimes they win the tug of war like outright. So we talk about ionic bonds versus covalent bonds as if they're two different things, like a binary. But I like to point out whenever possible that nature is not a binary. Binaries are simplifications that we use to teach kids complex subjects. Ionic bonds occur when the difference between the electronegativities is so great that one atom literally just steals the electron from the other. And that happens with metals and nonmetals because metals have very low electronegativities and nonmetals have very high. They're big hogs. So then you get an ionic situation. If you have two atoms that are very equal in their electronegativities, or they are identical, then you get equal sharing, and that is a truly nonpolar covalent situation. Then there's sort of the intermediate. So polar covalent is a covalent bond with ionic character. So it means that there's an unequal sharing. They're still sharing, but not equally. So one atom has a stronger pull, and so then we say it has a partial negative charge, and the other atom has a partial positive charge. I like to think of it as like a custody situation. When they're sharing electrons, it's like shared custody of those electrons. And just like, I don't know anyone else I'm a product of divorced parents. Some divorced parents share custody equally. Kids spend 50-50 time with each parent. And in some divorces, the kids spend more time with one parent than the other. So it's a sort of an uneven sharing situation. So covalent and ionic bonds are really just two things along a spectrum. They're not like completely, it's not a complete binary, but we do have this arbitrary sort of point which we draw the line and say, okay, it's no longer polar, it is ionic. Alrighty, so these different types of chemical bonds, again, just showing them in a different way. Nonpolar covalent bonds is equal sharing. Polar covalent bonds, you form these poles, these charged poles, and ionic bonds, you form completely charged ions that then attract each other because of their opposite charges. All right, ionic compounds form, anything that is formed of ions is an ionic compound, and we call these salts. So the classic salt, of course, is sodium chloride, but any metal plus a nonmetal is a salt, so something to remember. And salts always form these crystal lattice structures. So all salts are like crystalline solids because it's just a bunch of ions conglomerating together, attracted by their opposite charges. So salts will pretty much always be either in a solid state because they're crystals and they're all packed together, or if they're soluble in water, they will dissociate into their individual ions and they will be aqueous. All right, you can melt salt, you can heat salt up so that it's a liquid, but it's not common, and doesn't really happen at normal daily temperatures that we use in the real world. We technically don't call these molecules because they are large clumps, not individual units. So we say that they're made up of individual formula units. So NaCl, we say, is the formula unit, not a molecule. There's not actual molecules of just one Na and one Cl floating around. Covalent compounds, though, they do form these individual particles. And so we call covalent compounds technically our molecules. And covalent compounds can exist in all states. Covalent compounds there's way more covalent compounds out there than there are ionic compounds. Alrighty, so when we are drawing covalent compounds, we can represent their structures of those molecules in a two-dimensional format by drawing Lewis structures. I'm not going to reteach it, but here's how we draw those Lewis structures with bonds that represent two shared electrons and lone pairs that represent electrons that are not shared. And these are all just representative of the valence electrons of those carbons and oxygens. So Lewis structures are two-dimensional. That's an easy way to draw molecules and quickly represent them, but it's not realistic to how molecules actually are in space. They are three-dimensional. It's kind of like drawing a stick figure is not a very realistic representation of a person. People are three-dimensional. So this dash and wedge structure is one way that you'll see molecules. It's a way to draw molecules in a more three-dimensional way on paper, but you also will see them a lot in images and textbooks or in physically as ball and stick models that are taking up space. And so you can see that makes a difference in the spacing of the atoms. So when you have it drawn on paper, these hydrogens look like they're 90 degrees apart, but in reality, they're going to space themselves as far apart as possible because they do have electrons around them, and those electrons are all negatively charged, and negative charges, like charges, are going to repel each other. So they basically all want their personal space. And so we have this model for predicting the shape of molecules called the Vesper model, which has to do with valence shell electron repulsion theory, and it's actually VSERP, but everyone pronounces it Vesper. And so these are some of the different shapes that we have. So linear, trigonal, planar, tetrahedral, trigonal, bipyramidal, and octahedral. And these are the electron shapes. So those electron domains can be lone pairs or atoms. All right. If we are just looking at the molecular shape, the positioning of the atoms, we have a variety of different shapes. And this is just like a neat table that kind of shows you all the different molecular shapes for each of these different types, different three-dimensional options. So when we have a molecule and we want to assess whether it is polar or nonpolar, it's similar. We are looking for the presence of electron hogs. All right, so at least one polar bond means at least one electron hog, and that there is asymmetry. So some examples here. These two guys are not polar. Even though they have polar bonds, these arrows are dipole moments and show that chlorine is an electron hog. It hogs electrons from carbon, so there is a pull of electrons towards the chlorine, but all the chlorines are pulling equally in opposite directions, and so overall the molecule is not polar because of that symmetry. All of those equal and opposite bonds cancel out. Polar molecules are things that are not symmetrical. So hydrogen chloride, HCl, hydrochloric acid has a polar bond. There's an electron hog and a non-electron hog. Same thing with ammonia, NH3. It's not symmetrical. I mean, it kind of looks symmetrical artistically, right? If you drew a line down here, you could fold it and there is symmetry. But what I mean by asymmetrical is not all of the groups around the central atom are identical, because there are 3 hydrogens and 1 lone pair. So they're not 4 identical groups. Same thing with this carbon here. There are 3 hydrogens and 1 chlorine, so they're not all. So when we're talking about asymmetry, we mean if at least one of the groups around if one of the groups around the central atom is different than the others. There's not identical groups coming off the central atom like there are in these nonpolar examples. So this is going to come up in our first chapter, chapter 10. We'll review this as well again. We talked about in Chem 101, percent composition. So this is how early chemists actually figured out what substances, what compounds were made of. They were able to break it down into the individual elements and measure the mass of those elements so they could figure out the proportionality and then recognize what the chemical formula was. So percent composition, just like any percentage that you're taking, it's always the part over the whole times 100 to make it a percentage. And we had a cute little rhyme to figure out how to calculate our percent composition. It was percent to mass. So if you are given a bunch of percentages, you just turn the percent symbol into gram symbol, and then mass to moles by dividing by the molar mass. And you get the number of moles, and then you divide by the smallest, divide them all by the smallest number. And that is sometimes where the process ends, if you have all whole numbers, but if you don't have whole numbers, then you multiply till whole. So 3.5 is not whole, so we need to multiply it by 2, which means we need to multiply all of them by 2. So the chemical formula for this substance, K2Cr2O7. All right, we also talked about solutions. A solution is a homogeneous mixture of more than one substance, but where they're very evenly mixed. And so solutions are made up of two parts, at least two parts, a solvent and at least one solute. So the solvent is a thing in greater mass, the solute is a thing in smaller mass, or smaller amount. And another way I think of it is the solute is the thing that dissolves, the solvent is the thing that is the dissolver. Typically, when we think of solutions, we think of a liquid solvent and a solid solute, like water and salt, but they can be in any phase. Air is an example of a solution. It's a solution of multiple gases, so things can be in the same state. Reminders again about the difference between ionic compounds and covalent compounds. Ionic compounds, also known as salts. Covalent compounds, also known as molecules. And some reminders about acids and bases, which are types of solutions, common types of solutions. Water is our universal solvent because it can dissolve a lot of things. And when ionic things dissolve in water, they can conduct electricity. And so anything that is really ionic and dissolves completely into ions is called a strong electrolyte. Anything that is molecular, covalent compounds that are molecules, they do not dissociate into ions. They're not made of ions, so they don't dissociate. Those are non-electrolytes, and they will not conduct electricity. There are some substances that are weak electrolytes. Those are going to be either ionic salts that don't dissolve, that are not very soluble in water, or acids and bases, a lot of acids and bases, which are actually covalent compounds that are very polar. They're so polar that they actually ionize in water. So they're kind of in the middle of that spectrum there. Just a reminder of what this looks like from a chemical formula and a particulate view. When you have a solid salt like potassium iodide, when you put it in water, it dissociates into potassium ions and iodide ions. Those ions have charges, and we say that they are dissolved in water, but we say they're aqueous. So we don't have to have H2O written here. It's implied by the aqueous thing. And so the solid would be this crystal lattice structure of all the ions connected together. You put it in water, and they all separate out into individual ions. Same thing here with lead nitrate. Lead nitrate is one ion of lead and two ions of nitrate, so that subscript becomes the coefficient. In other words, the one lead and the two nitrates separate, so we have a bunch of individual ions here. And I think I color-coded them wrong here. There should be twice as many purples as there are oranges. So solutions have concentrations. Concentration is just the amount of solute per an amount of solution. And there are multiple different units or ways that we can measure amounts of things. So there's different units of concentration, and the most common ones In chemistry, the most common one is molarity because, again, moles are the central unit. So that is moles of solute per liter of solution. And then another common way is through percentages. So by mass percent or by volume percent. The mass of the solute over the mass of the solution, or the volume of the solute over the volume of solution. Dilution is something we commonly do in chemistry, especially if you are, making solutions and you want them to be a certain concentration. If you need to make 8 different solutions of different concentrations, that's, you can make it 8 different times, or you can make one concentrated stock solution and then dilute it. And so dilutions are common. And the dilution equation is here, M1V1 equals M2V2, or I like to say C1V1 equals C2V2. M for molarity, C for concentration. Molarity, again, is the most common one that we use, but it works for percentages too, or concentrations given in other units. So that's why I prefer C. Initial concentration is always high. Final concentration is always lower. The initial volume is going to be smaller, though, because you do dilutions by adding water. All right, so chemical reactions. When molecules react with each other, or atoms react, basically a chemical reaction involves bonds breaking and reforming. And it happens when molecules collide with each other hard enough for bonds to break, and then also in the right position for new bonds to form. So I like this little animation here showing that we have, and we can write these chemical reactions. We write a chemical equation, kind of like a math equation. Reactants are always on the left, products always on the right, and the reaction arrow shows the progression. And my plus sign is a little out of whack here. But so we've got these, this would be the chemical reaction. Sodium plus potassium nitrate reacts to form sodium nitrate plus potassium. And that is the particle view up here, just kind of representing it as particles, trying to kind of mirror this little animation here to the side. We can classify different types of reactions into different categories. There's combination reactions, when two things combine to make one, when a bond forms to connect them. Decomposition is the opposite. Single replacement reactions, those are my home wrecker reactions, where a single comes in and breaks a couple up and the couple reform, so the bond forms between A and C and leaves B out on the streets. And the double replacement reaction I refer to as the swingers reaction. This is usually two ionic compounds, so it's usually the outer and the inner are the ones that are recombining. And then combustion reactions are really important to know because they're very common and popular in chemistry and biochemistry, and that's when you have any substance that's carbon containing, usually carbons and hydrogens, and oxygen and heat. It will burn to form carbon dioxide, water, and additional heat as the products. So that's the basic formula for a combustion reaction. Right? When we are writing chemical reactions, it is important to write out the correct chemicals, the chemical formulas, but then we also need to make sure that the number of atoms on each side are balanced. And so that is where balancing equations occurs. With balancing equations, we are adding coefficients. These are numbers in front of chemical formulas in order to make sure we have the same number of carbons, hydrogens, and oxygens on both sides of the equation. So here we needed to add a 2 because we had more oxygens in our products than we did in our reactants, so we needed to add some coefficients here to get the oxygens and the hydrogens to balance out. Just a reminder when you're writing chemical equations that there are 7 diatomic elements. Hofbrinkel is the mnemonic I use the most, but there's also Have No Fear of Ice Cold Beer, or you can remember they make the shape of a 7 on the periodic table, and there are 7 of them, but don't forget about hydrogen over here. This is just a reminder, a quick reminder of the 6 strong acids and 6 strong bases. These act as, basically they act as ionic compounds. sodium hydroxide is an ionic compound. HCl, hydrochloric acid, some of these are not necessarily ionic because hydrogen is a nonmetal. So, but in this case, hydrogen is ionic in these. So strong acids and strong bases fully dissociate in water. They're strong electrolytes. They basically act as ionic substances. All the other acids and bases in nature are weak acids and bases, and we'll get to those this semester. When we dissolve things in water, when you put something in water that is soluble, if it is a ionic compound, it does dissociate, right, into its different ions to a point, right? There's a maximum amount. So if all of the solute is dissolved, that's an unsaturated solution. But if you've reached the maximum amount of dissolved substance, then we say that the solution is saturated. And once it is saturated, you start seeing solid precipitate build up. And that is because no more can dissolve. Well, actually, technically what's happening is it's a dynamic equilibrium. Ions are dissolving and being surrounded by water molecules, but then some of them are precipitating out, and they're doing that at the same rate. So you just can't get it to dissolve anymore because there's a maximum amount of ions already dissolved in solution. So a reminder here of the different solubility rules, which salts are very soluble in water, which salts are not very soluble. Insoluble does not mean zero solubility. It just means very, very, very small amount of solubility, something to consider, that it's not absolute. So precipitation reactions we did last semester, these are chemical reactions that happen in solutions where you have two aqueous solutions, so two salts that are soluble and are freely dissociated. When you mix them together, though, two of the ions form a non-soluble salt and they precipitate out. And so the precipitate is solid. It's the ionic compound that forms a solid. And then the aqueous ions are still dissociated and dissolved in solution, and we call those the spectator ions. So this is the molecular equation that demonstrates or shows a precipitation reaction, and then here's sort of the particulate view of what's going on. So when we are doing something like a precipitation reaction in real life, we want to isolate that precipitate, collect it, weigh it, and do some recipe math and some stoichiometry. We might need to do some conversions to figure out how much of stuff we have. And so an extension of the mole train map here is if we have moles of one substance and we want to know how many moles of another substance we can make, we can do that using our balanced equation. So our balanced equation gives us another essentially conversion factor, which we call the mole ratio, and that's just the coefficients, the ratio of the coefficients of A and B. So, and we can extend that if we have grams of A and we want to know grams of B, we just need to go convert to moles first using molar mass, then use the mole ratio, and then use the molar mass of B. All right, we can also go from grams of A to particles of B. We could also, since now we're working with solutions, we can use the volume of the solution and the molarity, the concentration of the solution, as our conversion factor. So maybe we have the volume of solution A, and we want to figure out the grams of precipitate that we're going to make. And so this map helps us to figure out how much reactant we need, how much product we're going to make, that kind of a thing. We also have another conversion factor that I added, which is density, which can allow us to go from grams of solution to volume of solution, that kind of a thing. So with stoichiometry is just recipe adjustments in chemical reactions. And just like with any good recipe, you might have limiting reactants and excess reactants. So the analogy was making some sandwiches. You have bread, you have meat, you have cheese. How many sandwiches can you make? Which thing is going to run out first? So in this situation, this is the recipe for making a sandwich. You need 2 slices of bread, 3 pieces of meat, 1 piece of cheese. If you have this 6 slices of bread, 12 pieces of meat, and 5 slices of cheese, you're going to be able to make 3 sandwiches. You'll have leftover meat and cheese. The limiting reactant, though, would be the bread. The bread is the thing that's going to run out first. The bread is the reason you can only make 3 sandwiches. Your theoretical yield is 3 sandwiches. That's the most amount of product you can make. And so the limiting reactant is the name of the substance that's going to run out first. The theoretical yield is the amount of product that you can make from it. And then you can also calculate how much excess reactant you have. So that is stoichiometry. In chemistry, and even in cooking, sometimes you don't get as much as you expect to get. Your yield is usually slightly less than 100% of the ideal or theoretical value. And so theoretical yield is what we calculate we should be able to make. The actual yield is what we actually make. And in this analogy, it has a mouse eating a piece of meat, but maybe you're making the sandwiches and you drop a piece of meat on the floor and the dog eats it, right? So you don't actually end up making 2 sandwiches. So same thing in chemistry. So when we do, chemists, like an analytical chemist, when they're doing a chemical reaction in a lab and they're trying to actually isolate a compound, they will calculate their percent yield. And obviously the higher the percent yield, the better skill was involved. And very precise skills and techniques are involved in order to increase percent yield. Also, some reactions just naturally have higher percent yield. So, and where we use stoichiometry, where we did it last semester in gravimetric analysis, so like when we did a precipitation reaction, and then we collected the precipitate on a piece of filter paper, we dried it out, and we were able to weigh and isolate it that way. Another way that we use stoichiometry is in titrations, and that's something we're going to do this semester with acids and bases. It's how we can determine concentration of acids and bases using stoichiometry, math. And then now we're into the gas laws. So gases are particles that move around very quickly, and they are not sticking together. They are bouncing off each other, and they follow this, they sort of based on this kinetic molecular theory of particles, that gases move very fast, that when they collide, they just bounce off each other, that they really don't have any attractive forces holding them together, and that the higher the temperature, the faster they move, essentially. And so there are a number of gas laws that were discovered. Relationships basically between volume and pressure of a gas. So the more pressure you put on the gas, the lower the volume. So you push down on that piston. You lower the volume, you increase the pressure. So they are inversely related. When one goes up, the other goes down. But temperature and volume are directly related. If you increase the temperature, you're going to increase the volume as long as that piston can freely move. If the piston does not move, if you have the piston locked in place and you increase the temperature, then the pressure will increase. So pressure and temperature, volume and temperature are directly related. One goes up, the other goes up. Each of these gas laws, individual gas laws, are named after somebody. But we can combine those relationships into one gas law that we call the combined gas law. So these are the individual gas laws written out, those relationships, and the combined gas law says that P1 times V1 over T1 equals P2 times V2 over T2. And important note, when we're doing this, temperature has to be in Kelvin, because Kelvin is the only absolute scale of temperature. They're the only scale where all the values are positive values. So make sure that you always have temperature in Kelvin when we're working with gases. We also have the ideal gas law, which is also a conglomerate combination of those individual gas laws. So the ideal gas law is sort of like the master equation that really you can use for all things. And PV equals nRT, or piv nert, I like to say. Just remember that each of these things have to be in the right units, and those units are determined by our gas constant R, which is in units of liters times atmospheres per Kelvin times moles. So that means that temperature needs to be in Kelvin, moles need to be in moles, volume needs to be in liters, and pressure needs to be in atmospheres. Ideal gases behave in an ideal, like in order for them to follow these behaviors of kinetic molecular theory, for all those things to be true, they behave ideally under circumstances where it's high temperature and low pressure, and they can move fast and they're bumping off each other. As we lower the temperature and or increase the pressure, the particles start getting closer together, they're slowing down, they're getting closer together, and they can start having attractions to each other, and start behaving more like liquids than like gases. And so that's the difference between an ideal gas and a real gas behavior at lower temperatures, higher pressures. And then this is the master version of stoichiometry of the mole train with gases added in. So we can use PivNert actually as a conversion. We can, if we know the volume of a gas and the temperature and the pressure, then we can figure out how many moles of gas we have and do stoichiometry that way for reactions where we are producing gases and we want to figure out how much gas we're going to produce. So we did that in lab last semester too, where you had to figure out how much, you had a solution of vinegar and you had solid baking soda, and you had to figure out how many grams of baking soda and how many milliliters of vinegar you needed in order to produce a certain number of moles of gas that you needed to fill the volume of a balloon. So practical use of stoichiometry there. Another part of gases was Dalton's law of partial pressures. So when we have mixtures of gases, the mixture total, there will be a total pressure that's exerted by the gases, but the pressure that's exerted by each of the gases is proportional to how many moles of gas, each gas there are. So the total pressure of this gas mixture is equal to the partial pressure of each of the three gases it's made of, and the partial pressure is just the mole fraction times the total pressure. So the number of moles of that gas over the total number of moles is the mole fraction. Last thing we did this in Chem 101 was thermodynamics, so studying the transfer of energy. There's different types of energy. There's mechanical energy that we use to, like, pedal a bicycle. Thermal energy is the one that we do mostly in chemistry, deal with mostly in chemistry. That and electrical energy actually we'll hit on this semester. Sound energy, radiant energy, a little bit more in the physics realm. Some forms of potential energy. So kinetic energy involves movement of particles. Radiant energy, the particles are photons. Potential energy involves stored energy, sort of that can be released. So nuclear energy, when things decay and gives out, like, radiation. Chemical energy that we use to power things like batteries involve chemical energy. Also, we power our own bodies by eating food and getting chemicals from breaking bonds in the molecule, the chemicals of the food. So anyway, the first law of thermodynamics is that energy cannot be created or destroyed. It can only be transferred. So, for example, I'm going to skip ahead here. If you have two blocks of metal, for example, that are two different temperatures, all right, and you put them together, there's no, in a perfect system where all energy is transferred from one block to the other, there's no disappearance. The energy is not destroyed, it's only transferred. So the heat is transferred from one thing to another. So an energy of a system can go up or it can go down, depending on, I'm going to skip this part. Energy is a state function, so it doesn't matter how you get there. It doesn't matter the path you took. It just matters what the final and the initial were. And so anytime we see delta in chemistry, that's a change, and that always means final minus initial. And there should not be a delta here. It should just be change equals final energy minus initial energy. Another equation where we see delta here is in calculating the heat of a substance. So the amount of heat in a substance is going to depend on its mass, how much of that substance you have, what the specific heat of that substance is, and different elements or different substances have different specific heat. Specific heat is an intrinsic property like density, and the change in temperature. So this is the equation, I call it Q equals MCAT, that we use to figure out how much heat is absorbed by something when its temperature goes up or down. You can also use it to figure out what the specific heat of a substance is and identify it. So there's lots of ways lots of variables we can solve for. All right. But the concept of thermal equilibrium is that heat is not created or destroyed, it is only transferred. And so if you have two substances and you put them together and heat is transferred from one to the other, they will ultimately reach the same, heat will be transferred until they are both at the same temperature, and then no more heat is transferred. And so the way that we can write that sort of mathematically is that the heat that's the hot, A is the hot block here, B is the cold block. The heat that is lost by A is going to be equal to the heat that is gained by B. And so we can use those MCAT equations and set them equal to each other in order to figure out what the new temperature is going to be, what the temperature change is. And that is essentially how calorimetry works. It's how we measure the heat of different reactions. Is we basically conduct those reactions in a sealed container of water, and we measure the temperature change of the water. The heat that is gained or lost by that water represents the heat that is lost or gained by that chemical reaction. So calorimetry is how chemists measure the heat that's given off or absorbed by different reactions. We call that enthalpy. Enthalpy is the heat of a reaction, the heat of a chemical reaction, as opposed to the heat of a block of metal that's absorbing. That's just like a physical thing. But so for chemical reactions, we don't call it Q, we call it delta H. It's so we call this enthalpy, aka the heat of the reaction. And we can draw these reaction diagrams, right? So if this is energy on the y-axis and this is like time on the x-axis, originally we start out with reactants in a chemical reaction, and then the reaction happens, bonds break, and then reform into different compounds that have a different amount of potential energy in their bonds. All right, so if this is and so the heat of reaction can be read off of an energy diagram. It's just the difference, again, delta, final minus initial. It's the difference between the energy of the products and the energy of the reactants. Since it went down, this will be a negative value. All right, so changes in enthalpy can be negative or positive. A negative delta H, all right, where it's a downhill energy diagram, is an exothermic reaction. It's giving off heat. That's what that red arrow is, giving off heat. It's releasing heat into the surroundings. And if it's an endothermic reaction, it's overall an uphill reaction. The products have a higher energy than the reactants, and heat is absorbed in that reaction. You see this little bump, no matter whether it's endothermic or exothermic, there is always an uphill initially. That's called the activation energy. It's like the little push that you need to get it started. Think of a ball sitting on the top of a hill. It's not going to roll of its own accord. You have to but it doesn't take a lot of energy. If it's on, the top of the hill, you just give it a little tap and that'll get it rolling, and then it goes downhill on its own. Whereas if it's at the bottom of the hill, you have to give it a big push to get up the hill. So that's my analogy for activation energy, and we'll learn a little bit more about that this semester. And so chemists can measure the enthalpy of chemical reactions doing calorimetry, measuring it in a lab, but there's also some sort of just on paper ways that it can be calculated based on calorimetry values that are already existing. So calorimetry that's done at standard state, which is 100 kilopascals and 25 degrees Celsius, are available. There's reference tables for the heat of formation of a variety of different compounds. So the heat of formation is the enthalpy for a reaction that is the formation of a compound from its elements in their standard state. So carbon dioxide being formed from carbon and oxygen. The heat of formation for NO2, nitrogen dioxide, is from nitrogen and oxygen. So nitrogen is N2 in its natural state, oxygen is O2. So to make 1 mole of NO2, you need half a mole of N2 and 1 mole of O2, essentially. So that is this sort of definition of the enthalpy of formation. And so that's been determined for a variety of different substances, and you can look them up in reference tables in any textbook. And so then if you are given a chemical equation and that equation has not been performed in a calorimeter, we haven't actually measured the heat of that reaction, we can figure out what it would be under standard state conditions anyway, by using this equation, that the heat of the reaction will be the heat of formation of all the products minus the heat of formation of all the reactants. So if we have this reaction here and we go to that reference table and we look up the enthalpies of formation for each of those substances and we write them here, and I didn't do the math down here, but we would take, it would be the products, the heat of the products would be 2 times negative 207.4 plus 91.3, and in brackets, then minus the heat of formation of the reactants, 3 times 33.2 plus negative 285.8, and that would give us the heat of our reaction. Sorry, I didn't solve it on here. All right. Other manipulations that we can do of reactions on paper to manipulate or figure out the heat of reaction without actually doing a lab to measure it is if you reverse a reaction. Oops, I'm on number 2 here. If you reverse a reaction, then you reverse the sign of the reaction. So if you have an endothermic reaction with a positive enthalpy, if you flip it and you make the products the reactants and the reactants the products, then it becomes an exothermic reaction, but the same amount of energy, right? If you multiply a reaction, so if you have twice as many moles of a substance, you're going to make twice as much heat. So that makes sense. If you multiply the reaction, if you multiply all the coefficients by a value, you're going to multiply the enthalpy by that value. And then lastly, we can add chemical reactions together. This is called Hess's law. And if we do that, we can add their enthalpies together. So for example, if we know the enthalpies of these 2 reactions, but we don't know the enthalpy of the sum of the 2 reactions, we can just determine it mathematically on paper. And that is the end of my Chemistry 101 review. To jog your brains just a little bit, some of this stuff we will be revisiting, and some of it we might not be, but I'm hoping that it helped you. And oh, and if you watch it at the end of the first semester, this would be a great review video for the end. So, the end.